to do that sometimes. And then we'll go from there, and I'm gonna minimize all your faces so I can see more of my screen. But if you need anything, just holler and let me know. We'll go with it for right now, for the folks that are here. And then if things go well, we might be done just a smidge early, so we can have a good time, get some early sleep and all that other good stuff tonight. A lot of folks in my other classes have to work over the weekends and things. So if that's the case, thanks, and I'm sorry too, but we'll see how it goes. So today's topic, all right, just to kind of start, is basically learning to read the stories in stone and kind of geologic time and understanding the principles of geology. So I feel like we're going to kind of do a little brief history of the Earth, try to get a sense of place of where we are in Earth's history. And then once we do that, we'll give you a few principles to help us start figuring out how we know what we know. And then next week, we'll start adding dates and stuff like that to it, so we can really know. I'll show you guys will really know what we know or how we know about the ages of rocks and what has happened in Earth's history and stuff like that. Because right, nobody in human history was alive even 500,000 years ago. Modern humans didn't exist then. So how do we know what happened? And that's what we're trying to figure out here. And that's what I'll be sharing with you, and you guys will be figuring out and playing with. And I think it'll be kind of fun. So that's where we're going. And I'd rather be in the mountains here this weekend, right on the east side of Yosemite, but closed, cannot go. So we're going to start out. I have a little bit of geoscience in the news. There's a lot that's happened since last Friday. We'll talk about that geologic time activity, a brief little lecture about the history of the Earth, relative dating activity, and then your homework. I have the little reading that you can do as a follow-up at the end of class. It might help you with your sketch notes a little bit. It's not like a required thing, but it's there for you as backup if something I say isn't super clear. And then for the sketch notes, there's a thing called a gigapan sketch, and I'll show you that at the end. But it's a really cool technology that allows you to zoom in to a really like an outcrop or like the side of a road cut basically, but you can zoom in pretty close and see some pretty fine detail. And you're just going to make a little cartoony sketch of one of these at the end. And don't worry, I'll show you how to do it. It's not supposed to be stressful. You guys aren't professional geologists or anything yet. So don't worry, I'll show you what I'm expecting of you. And I know it's your first time doing this stuff. So don't stress out that it's got to be perfect or anything. And then remind me to do sunshines and blues. I forgot at the end of my other class this morning. So remind me if I forget to do sunshines and blues. So speaking of which, it looked like last week, everybody enjoyed most of the stuff we did. The one person was upset that I destroyed my kid's Minecraft world, and I totally forgot I did that. He's forgotten, thankfully, by now, so we can move on. And then somebody also said, allow time throughout the class for questions. And with that one, all I can say is just holler. If you have a question, interrupt me or put something in the chat or something like that, and we'll stop and take the questions. All right. I'm not trying to just blast through things without folks understanding. So yeah, if you ever need a question, just let me know. I can't see like all your faces and stuff. So if you're raising your hand, sometimes that's a little hard, but if you do the participant window, like leave like a thumbs up or a hand raised or whatever in that, or you can just chat, whatever you need to, unmute and say, hey, I have a question. I'll totally stop. All right. So don't be afraid to ask if I guess that's the key here. So, and I'm sorry if you felt like you couldn't ask last week. That was not my intentions for sure. So with that, oops, maybe. Oh, my computer just froze. Hold on. Okay, let's see here. So it froze. Now it's unfrozen. So today for the sketch notes, I know there were a few folks that weren't here last week, and some of the instructions are on how to do this totally and to set everything up are there. But what we're going to be looking at tonight these are kind of the big ideas here that we're going to be looking at tonight, and the things that I'm expecting that you guys might want to add on your final sketch notes. And just to reiterate, these sketch notes are generally due like at the beginning before the next class, like so a week from now. It's taking me a little bit longer to organize and get all these links and stuff together. So everybody's going to have a couple extra leeway days to get like the first week's worth of stuff done. And once we get that done, that's piece of cake, and we'll go from there. So don't stress if you didn't have everything finished the first time, but remember, the things that you want to put on your sketch notes are basically these themes and ideas that are on kind of these templates. And you can find these in the modules section of Canvas, right over on the left-hand side. If you click on modules, week 2, if you scroll down, you'll see, oh, sketch note template, and you click on that, or I think it says weekly sketch note template or something. And all of the different things that you need to have on there for each week are there. All right. So for today, we're going to do like a quick sketch of the Earth's timeline and the major events. The thing we're going to be looking at and playing with is 30 events long or something. All I need from you on this one, though, and I didn't put it on here, but it's on your template on your class. So it's only like 9 or 10 ideas. You don't have to do the whole entire thing, but 9 or 10 big ideas. That's kind of the first thing to sketch. And then a quick summary and a few sketches of how the Earth formed. I'll spend a little bit of time showing you how that happened. All right, so the first part's going to be interactive. This little part's going to be like 10 or 15 minutes worth of lecture. And then some of the things to think about is like, how is the real geologic timeline grouped compared to what we made? What separates one era from the next? We'll think about that, and we'll talk about that. So you have no clue what that means yet, probably, unless you've had a geology class of some sort before. But don't worry, we're going to be talking about it. We're going to be thinking about it. And this is just where you kind of put your thoughts at the end of class. All right. And then we're going to be doing some relative dating principles, and we're going to see 8 different concepts or principles of relative dating that helps us. If you look at this funny cartoon down here, helps us organize what happened in history. So this is looking at like a slice down through the Earth like that, looking at the different layers of rock and things that are happening to it. It's kind of unique and kind of crazy, and you guys are going to be able to play around in groups with each other to put these in order, following some of these principles over here. So for these, you can just kind of list what the 8 different principles are, add a little sketch for each one or something like that, a quick little description, and then you can draw an arrow to where that principle is used in a relative dating rock sequence. And this is what I'm talking about right here. All right. So you're going to draw a quick little cartoon of maybe this or a different one, and kind of do everything that happens here. So by the end of tonight, you'll be able to look at this and tell me the order of what rocks came first in this sequence, which ones are the oldest, which rocks are the youngest, which things happened last in Earth's history, and even a little bit of how it happened. So we're looking at the big picture first, and as we progress through the weeks, we'll kind of like zoom in on the rocks a little bit. And then when we finish zooming in on the rocks, talking about earthquakes and volcanoes, we'll zoom back out, go and talking about the atmosphere and the ocean and things like that. And then we'll zoom really far out and apply all our knowledge at the end of the year to the solar system, and apply what we know here to what we see out there. All right, so that's one part. And then the very last part here is this giga sketch. And honestly, it's probably taking me more time to explain than it's going to take you guys to do. But there's 3 different links here that you can click on, and it takes you to a gigapan that I'll show you at the end. And I'll show you how to make this very simple sketch, all right, and do these things at the end. So that's where we're headed tonight. I do want to show you a few resources. Luckily, I mean, the Caldor fire, we talked about it last Friday. So much has happened since last Friday. It crested the Sierras. It went down near South Lake Tahoe, but like a miraculous firefight ensued. And luckily, not too many structures were burned. None down in South Lake Tahoe or Myers, but there's a few up near the what do you call it? The passes up there. And so there's this link I put in here. The green lines that you see streaking across, those represent arrows of wind or how fast they're going. So anything that's green is like 10 miles an hour or less. And the more faded it looks, the weaker the winds are. But you can see kind of this is the perimeter of the fires, and anywhere you see A red asterisk is where a satellite picked up a really hot spot in the last time it passed over. I think it was like 6 or 7 hours ago. And then these big red pixels here, these update every 5 minutes, these big ones. So there's a little bit of fire burning over by Kirkwood right now, but it's not too bad. The fire conditions have gotten a lot better, and it's not burning too hot, thankfully. And then the other fire of note up here is the Dixie fire. And it doesn't look like much. I mean, there's still some intense stuff happening over there. But the thing I want to show you is the Dixie fire is the largest single fire in California history. It's 868,000 acres. So, I mean, it's just massive. And this kind of shows you where it started down here. It's pretty interesting. It started way down in the Feather River Canyon when a PG&E tower fell and a power line sparked, and it just went up and it burned all this way. And what's kind of cool is called these color progression charts, is as the colors change, those represent different days. And you can see the days that each color represents down here in the bottom. And you can see how it's just kind of spread out in all directions everywhere out there. It's burned a lot of Lassen National Park. It's burned a lot of areas that I grew up walking around when I was a kid, and in the winters and the falls and stuff. So it's kind of it's an interesting personal one. But the Caldor fire is only a couple 100,000 acres at this point, which is up until 4 years ago would have been like one of the top 5 largest California wildfires. And now it doesn't even make the top 10, which is pretty intense to think about. There's also another website I want to show you, and that's Purple Air. And so these are all kind of like nothing you need to take notes on. This is just an FYI because we're going to be coming around and talking about this in class. And I think it's good for you for your personal lives that you might want to know. Purple Airs are all these little monitors that hang up on houses or buildings and stuff like that, that shoot lasers through the air and can tell how much particulate matter is in there. And that's what you see here. And every single one of these reports every single minute back to the internet. And if you go and click US EPA in this little conversion here, give it a second. There we go. It converts it and lets us know what the air quality is. And so for right now, it's kind of like moderate air quality. I still wouldn't want to be up in some of these areas around Tahoe, which is like 224. But even as recently as like 2 days ago, when the fire was still going strong, the smoke down here was over 700. And basically anything over 500 is pretty much off the chart of extremely unhealthy, like hazardous is what they label it. So 224 is still extremely unhealthy and in kind of the hazardous category, just not 500. So it's getting better. And we're going to see in just a few minutes that I think we're going to have about this same quality of air throughout the rest of the week. And the only unfortunate part is it's going to get a little bit warmer. All right. And so there's a really cool Twitter bot that you guys can follow on Twitter if you want. It's called the HHR Smoke Bot, and it basically has smoke forecasts for 12 hours and shows you where the smoke is going to blow and stuff. So you can check that one out if you want. And I already showed you these maps. In case you didn't know, there are awesome wildfire cameras. If you want to get into the game, you can click on that link and wow, it looks like the fire is kind of right over there. But if you click on these different cameras, you can see what the fire conditions look like up in the mountains right now where they're trying to fight this. So maybe what will it look like if I go from way far away? Oops. So if you go from way far away across the mountains, across Nevada, you can see the smoke has settled down pretty low and it's a little clearer up high. So just something to think about, something you can see in the previous days. This is what we watched to see where stuff is burning and blowing up, but it's kind of subsided. So that's just something kind of an FYI site for y'all. A few pictures of last Saturday and Sunday when the Caldor fire moved down through Echo Summit on Highway 50. It did burn some cabins, not as many as we thought was going to happen. And basically all the town is safe underneath, which is great. Still 45,000 people or so evacuated. And then we talked about Hurricane Ida. We said, oh, watch out, there comes Hurricane Ida. And maybe if you saw it in the news, it hit hard, right just kind of west of New Orleans, right around in this neighborhood. This map is from Tuesday. It hasn't really changed much. But basically it came on shore as a Category 4 hurricane, almost 150-mile-an-hour winds, sustained for long periods of time. It literally blew all the water from the bay, the Gulf, into back up the Mississippi River, and the Mississippi River actually kind of stopped flowing for a little bit because so much water was pushing up against it from the ocean. And some of these storm surges, or that water getting piled up, was 12 feet deep in areas. And when you live in a place that's only, 3 or 4 feet above sea level, or in some cases below sea level, if that storm surge goes over a levee or something like that, your whole city gets kind of drowned. And that's what happened with a lot of folks here. And the red that you're seeing are power outages. So they had a big transmission line go out across the Mississippi, and all these people are going to be out without power for at least another 2.5 weeks, from what I've heard from my friends that live in New Orleans and teach at some of the universities down there. And this is one of the aftermaths of that. So that was just bad. And then what's today? Friday. So on Wednesday night, all of that storm, the remnants from Ida, went up the East Coast and was just loaded with tropical moisture still. And it collided with another weather system to basically squeeze out all of that rain. And it all dumped over the most populated cities along the East Coast. New York City had almost 7 inches of rain in 6 hours. To put that in perspective, that's almost the entire amount of rain we've gotten in Turlock this entire year. So you might have seen pictures of flooding in like subways and stuff. And in Philadelphia, this is New Jersey on the left yesterday morning, and then this was Philadelphia yesterday morning. The rivers are just huge. And one of the things we'll talk about is when you pave over a city and you have impervious layers, there's no place for the water to infiltrate. So it just runs right off and like into rivers and things flood. So we'll try to address and figure out how to do smarter city building in the future, and what we can do to address stuff like this now. But it's pretty intense, and it's pretty, out there. And we're learning as our climate keeps warming up, what's kind of interesting is that all the new models and stuff like that and the studies they show, climate change's fingerprint is going to make these types of events more common. All right, so climate change doesn't cause crazy disasters like that. That's a daily weather type thing. But climate change is like loading the dice, or like putting a weight on the bottom of the dice. And when you roll it, you're going to have a number come up more frequently. Well, because we're putting more heat in the atmosphere, more moisture in the atmosphere, these are going to be more frequent as we move forward, these types of storms. So these unprecedentedly huge types of storms. And we got to be ready for stuff like this in California too. And we'll talk about that towards the end. So holy moly, not every week is there so much stuff going on. And there was even on Tuesday, a couple little magnitude 4.5 earthquakes right before class. So we talked about that too, but no big deal for right now. So, the West Coast, East Coast, South Coast, everybody's getting walloped right now. And Alaska's getting snow. So fall is right around the corner, and something to think about. Whew. Okay, so sorry, I talked a lot, but here's what we're going to do. We're going to talk about this geologic time now, and we're going to switch gears. And now this is where all the stuff that's going to be on like the sketch notes and stuff starts. Those other things, you can download these lecture notes and click on them, and those are the links. But I think they're useful things that you should be able to use in your life to make decisions about, oh, it's bad air, I don't want to go run today, or something like that. So that's what we're shooting for. So in this geologic time, here's what we're going to do. We're going to start out with a group activity now. So I'm going to send you a link, and in just a minute, I'm going to send you that link. Don't let me forget to send you that link. But it's going to go to this thing, which is called Miro. And it's like a Jamboard, but it's kind of like a Jamboard on steroids. All right. It's a pretty cool thing that I think you guys will enjoy playing around with. So you'll notice if I just click on kind of the blank side here, I'm not trying to get you sick, but if I click and drag, I can drag that anywhere I want. If I zoom out, I can keep zooming pretty far. It's basically an endless board. All right. So it goes on forever, but we're not going to do that. But you also can zoom in like this. And if you zoom in, you can see lots of stuff all over the place. So you can zoom in and zoom out. It's much more like high resolution than Jamboard, something like that. And what I want you to notice here is that there is a timeline. And at the right end of the timeline, it says the present, or today, you are here. This is the end of time, or where time has gotten to so far. It's us today. And then this timeline goes back all the way to the end down here where it says 5GA, and GA stands for giga annum, which is also the same thing as saying 5 billion years ago, which is written out with a 5 and 9 zeros at the end. So all three of these things mean the same. It's just three different ways of representing 5 billion. All right. So 4.5 billion, 4. So you notice each one of these is 500 million years in a time gap here. So here's what y'all are going to be doing. I'm going to get you into groups of 3. And what you need to do is you can just, if you double click on this, this is also like a sticky note, like in Jamboard, just type your names in group number 1 right after you do that, or right after you click on it and edit it. That's what you need to do. And then if you click the arrow on the left, it's like the select arrow right there. That'll allow you to pick a card, any card, and move it around. So my goal here is like group 1, these 3 cards belong to group 1, group 2, these cards belong to group 2, etc. I don't know that we'll have all 10 groups here. We'll see, maybe we will. But that's how you move those around. You can zoom in and click and drag and move, and that's totally fine. But what we're going to do as a group is you're going to take these 3 cards and you are going to place those 3 cards where you think they belong on this geologic time scale here. Oh yeah, so if people are driving, that's totally fine. Hopefully you can catch the interactive version online a little bit later on and see it in the video if you need to. So you'll click on this, you'll move it to wherever you think it needs to go as your group talks about it. And here's another neat trick that you can do with this Miro board. So if you take this card and you want it to point to a very specific spot on here, because remember, this represents almost 500 million years from point to point, which means, each one of those small little bits is 10 or 20 million years or so. If you want to make it more specific as where it's pointing, if you click this longer looking arrow with a small arrowhead, it's called a connection line. If you click that, then you click the blue dot on your card and then go down to the line down here, the timeline. What that does is it kind of anchors this little arrow point so it shows exactly where you think it goes. All right, so that's another thing you can do. You don't have to. And if you want to get rid of that line, just click on it and hit delete and it'll go all the way away. All right, so I think those are the main ones that you need for this. Is just this, click the arrow to select it and move it. And if it's not highlighted in blue, that means you drag this part around. But if you click it and then the arrow becomes highlighted in blue, that means you can drag the cards and stuff. So I'm going to put you in groups, and all you need to do is organize these 3 cards and place them where you think they go. This should take about 6 or 7, maybe 8 minutes or so. And once you're doing that, once we're done with that, we're going to come back. We're going to have a little discussion about it, and then we'll move forward about how do we think we know what we know. All right. So breakout groups, here we come. And let me see here. And if you're driving and you're in a breakout room, you can just listen to the chatter, I suppose. And that's what we're going to be trying to do here. So I'm going to put y'all in 7 breakout rooms. There's only 21 of us or so. And one of the things y'all can do is you can share a screen. Let me make sure I got everybody's screen sharing on. Yep, everybody can share a screen. So if somebody wants to share a screen, that's totally fine. Or if everybody wants to look at their own while they're talking with each other, that's great too. But just do me a favor and try to interact the best you can with one another. If you feel like somebody's being kind of quiet, you can ask them some questions to ask their opinion and things like that. So let's see how it goes. And I'll be done talking for right now. And we'll do this for about 6 or 7 minutes. Oh yes, the link. See, I told y'all you needed to help remind me. Thank you. So let me get that link, copy the link, put that in there. And now everybody should have the link. So let me make sure everybody, I see little arrows popping up in here first. All right, let's see, there we go. I can see, look at all your little like flies zooming around there, which is kind of cool. All right, perfect. So now you guys can do that. And don't forget, remember on the left-hand side, that blue arrow or the arrow, if it's blue, you can select the cards. If it's not blue, it kind of moves the board around. And if you're on a device that has touch, I think the zooming is pinching or pinching out, or zooming out and zooming in by pinching together. Okay, so here we go. Here come your rooms. Say hi to each other, and we'll be back in about 7 minutes or so. So this is not to overthink it, but just have some quick ideas and then place it where you think it goes. Turn on the air conditioner because it's hot. Oh, hi, Sarah. Are you here?
Hello, Professor. I had to take my dog to the vet and I was trying to use the app on um app, but it wouldn't let me log on to Zoom, but I'm finally home.
Oh, okay. Yeah, no problem. Is your dog okay?
No, he was feeling like he was acting weird, but they told me because he's a senior citizen, he's a dog on the screen on my picture.
Oh, okay.
Because he's a senior citizen, apparently he needs to have his teeth removed. That's what's causing him pain.
Oh, no.
I know. I knew there was something wrong, but I never thought it would be. I never thought, Papi, be quiet. I never thought it would be dental.
Oh, well, I
It
hope
just took
that's not.
longer.
How old is he?
He is 11.
Oh,
I've had
man.
him since 2010.
Wow. That's a good long age.
Yeah, he's my senior citizen.
So do you have to give him like soft food and stuff now?
Yeah, and then I had to set up the appointment for the teeth to be taken out, and because he only has a few left.
Oh,
So I didn't think the appointment was gonna, I thought I would be back before class started, but I wasn't.
yeah, not a problem. Animals and pets, they do funny things sometimes. So
They
we are
do.
just in a little breakout room with different groups. So is it all right if I put you in one of these groups? What we're trying to do is there's a whole bunch of items from Earth's history on here, like when dinosaurs were, first flowers, something, and everybody's just making a guess of where they think those different items go on a timeline.
Oh, fun.
I think it's kind of neat. So if you want to join with one of them and maybe they'll share a screen, and actually here um, I'll put the link in the chat again so you can open up what they're working on. And they'll have probably about 4 more minutes or so of working on that before we come back and talk. So,
Okay, I was also,
oh
Joseph,
yeah, go ahead.
I was also wondering if you were able to see my emails. I know that you're busy with a lot of
Oh,
stuff
is this
going on.
the link about it wasn't on your Google Drive?
Yes.
Yeah, I just saw that again this afternoon. So how about if you stick around, can you stick around really fast after class and we'll see if we can figure it out? Or
Yes, of course. I have no problem doing that.
okay,
I
yeah,
just want to get it situated because I know that sketchbook is like a big part of our grade and I don't want
yeah.
to miss out on anything of
No, don't stress. You're not gonna be late. It's taken me a few bits to get everything organized and stuff here, so we'll have a few extra days. So don't worry about it.
Oh, perfect. Thank you so much, Professor.
Yeah. So let me get you in a group here and see where we can go from there. Okay.
Okay, perfect. Thank you so much.
No worry. Hope your dog is okay.
Thank you.
All right, everybody. Welcome back. Welcome back. So here's a couple of things I want to think about or have you think about. And I'll have anybody that would like to share out if you'd like to share out. So that would be great. But some things, a couple of questions here is like, how did your team decide where to place the cards? And did you agree or disagree with other groups' placements or even within your own group? What were your sense of feeling here? And what are some of your ideas we go back and look at this timeline here, you guys, how did you feel? What did you do? How did you do it? Do you agree with folks? Do you disagree? Anybody that wants to chime in, feel free, or you can chat it, you can unmute, however you need to.
So for
So
group
our-
5, oh, go ahead.
I was just gonna say that we were kind of going based off just solely our photos, obviously, because you want to focus in on what you're going to be working on. And then you realize that other people are moving their photos to where they think, and you have a rough idea of when yours was around. A rough idea, a very rough idea, I should add that. But then you're using the timeline and you have very little to work with. Like, let's say, obviously the ocean was there, but how do you know what was there after it? I don't know. It was very stressful.
So you zoomed in on your own. All right. So I think it was Ariel that was saying something again too.
Yeah, I'm in the same group as him, but we had like the first flowers. And so obviously like for flowers to grow, you need the sunlight, I'm assuming. And
Right.
so we kind of like went off of like when was the sun formed. So that was kind of helpful for that one.
All right, interesting strategy, good strategy. And then somebody says in the chat, this was hard to guess because we have years and not names, all right? But we're going to base the description on what others placed their cards as well. So some folks went off of what others were doing. Did anybody feel like you got your cards down and then you saw other people put it someplace else? Like, oh man, what do they know that I don't know? Maybe we should move it. Did any of those discussions happen? No? All right. So, oh, go ahead. Sorry.
I kind of thought about it. I was looking around. I was like, well, they're putting it there. I mean, I don't know if mine's wrong or theirs right. So yeah, we kind of just went off. Like we had the insects and then the moon and then humans. So it was like, oh, okay, you know.
Right.
Like humans. There was apes first and humans. So
interesting. All right. So there's some little bit of background knowledge there. So remember last week we spent the whole class talking about background knowledge and what we know and how that shapes and influences our perception of life and even reality in some cases, right? So this is our like starting point. This is our class's starting point of where we think things happened. All right. So this is where we are. And now what we're going to do is we're going to get back in our same groups, but I'm going to give you, and by the way, thank you for sharing, everybody that shared. I'm going to give you a special thing here. Not that special thing, this special thing. I'm going to give you some actual links, and I think it should open in the chat now like this. And all you need to be able to do is view. You don't have to edit it or anything. And in some of these classes, I had like more groups, so I doubled up on those. I thought I have all of the correct cards lined up with each one of the groups that you did, but I've heard there's a few that might not be lined up. So just find the card that you did and click on that. And basically what will happen is, let's say if you're in group 1 and you had banded iron formation, it's a link that takes you to and tells you about really quickly, oh, here's what a banded iron formation is. And oh, it's some of the oldest known rocks over 3,700 million years ago, or in other words, 3.7 billion years ago. That's what these banded iron rocks are. So you'd get that information and you go back, and what you're going to do in your groups now is you're going to find that whoever had the banded iron formation, like right here, weren't too far off. They had it at 2.5 billion, but they're probably going to go and take this and move this over to here and maybe put an arrow that says, oh, 3.7 billion years might be like right about here. Okay, so that's what we're thinking, and that's how this goes. And I'm sorry if I stole banded iron formation group 1. Y'all can find another one, like Burgess Shale still needs one, so you guys can do that one instead. But we're going to put that there, and we're going to see how does how do things change now that you're going to learn a little bit about these things. Just the 3 that you did, and then try to put them in the areas you need to. And if anything gets crowded, kind of like it's getting crowded over here, y'all can totally drag the cards down farther and then just draw a line up to the timeline. It's up to you guys, all right, and how you want to organize it. So now you'll have the information. We want to try to put these in mostly the correct order based on what we see, and then we'll go from there. All right, so I'm going to put you in the same breakout groups. This one will take, I think, how many minutes did I give y'all? Let me see. Keep clicking on the wrong one. This one I'm going to give you about 10 minutes to do. I think 10 minutes should totally be fine for the 3, and we'll see where you're at from there, and then we'll take a quick little break, okay, before we get on with the next stuff. So you have the link, you have all that good stuff. Here come the breakout rooms again, and go for it. Forgot to change the time. Danielle and Madison, you guys here at all, or? Awesome. helps to talk if I'm not muted. So great job again, everyone. I think I addressed most of the if there were a few misconceptions here or there. Like the one thing that I consistently, my camera slid down, I think. Well, the one thing I consistently notice whenever we do this with any class is sometimes the confusion between billions versus millions. So somebody will say, oh, Stegosaurus, 150 million, you know, and they'll go put it where like 1.5 billion or something like that. So it's like the number of zeros can sometimes, we just see the zeros and that's where we put it. So really interesting to think about is when we look at this timeline, if we zoom in here, right, here's the 500 million years ago and here's present. If we took from here to here and we like split it in half, that would be 250 million years. This would be about 125 million years. This would be what, 60 some million years right here. So 30 million some years. 15 million years would be like right at the end of the arrow. So kind of crazy to think about. 15 million years ago is still on the end of that arrow right there, which is just bonkers in my opinion. But yeah, hey, look at this. Y'all got this right. The Earth did form about 4.56 billion years ago. And then I'm going to slide the moon over just a little bit because that happened about 100 million years later. The Earth was there and then the moon formed and then we start getting oceans. So what are your thoughts now that you see kind of the actual dates and actual things? What are some thoughts you have? Maybe compared to pre what we had going in and what we ended up with, or were you surprised by anything?
Everything definitely migrated to the right.
Yeah, everything migrated to the right, right?
Agreed.
Like, what's that?
I was just saying I agreed that everything shifted from all the way to the left to all the way to the right.
Yeah, so we came into this thinking, man, things like life and all that stuff evolved a long time ago, and it totally did. It was a long time ago in our human conception of time, right? But when you look at it on the geologic time scale or the age of the Earth, life didn't really start going bananas until about 500 million years ago. That's when things just started taking off and multicellular animals started going nuts and things. So that's kind of when it happened. Right after this latest, we'll see this thing called Snowball Earth a little bit later on. But Snowball Earth was a time 600, 700 million years ago, somewhere in that neck of the woods, where almost the entire Earth was frozen and there's just maybe a thin little band of open ocean water near the equator. And we'll be seeing some examples of how we know that in upcoming weeks here. But banded iron formation, this is important because these rocks right here in the banded iron formation, they formed in seawater as a result of oxygen released by photosynthesis. So this was the first evidence on Earth in the geologic time scale that there was enough photosynthesizing bacteria and stuff that would allow rusting to start happening in our rocks. And that's where we start seeing it, is when there's oxygen, it causes iron to rust, and it makes these cool sediments where things fall out and make these really interesting patterns. All right, so if we were to take this and I would say, hey, I'm going to give you guys like 5 minutes. We're not going to do it, but if I gave you 5 minutes to chunk Earth's history up into like 3 or 4 different chunks of time, how would you divide that up? What might be some of the dividing lines for y'all of like, if we had to look at really 3 or 4 big chunks of time, where might be a good idea to like chunk these up? Like what would be a good dividing line to say, hey, this part of Earth's history was different than this other part of Earth's history? Any ideas? Based on what we're seeing here. So not the real definitions, but just what we're thinking about or what we're looking at here. It's a safe space. You can have ideas. There's no bad ideas. That's the one thing I want to say here.
This is
When the
probably a
moon
bad idea.
formed.
Hang on, my dog's barking.
That's right. No worries. Oh, somebody else was going while she's getting her dog. Who else?
Sorry, the dog said something. I said when the moon formed. things started popping off.
All right, so the moon formed, and then we have other things. So maybe we could put like a division line, a chunk right there. All right, where else might be? Do you suppose might be kind of another chunk of where things happened?
I was gonna say like when the planets form, but that's kind of like goes off with what he said with like the sun.
Okay, so that would be, I mean, so yeah, we could put that like right here, let's say at the beginning, and that's supposed to go by where Earth is. But yeah, the Earth forms right there. So that's the beginning. So that this could represent one chunk right up in here. So what do you all think? Do you think like if it looks like life is just kind of taking off and exploding right around here, and do you think this might be a good spot to put a dividing line? Because there's like a whole bunch of nothing between here and here, not very much anyways. Would that be an okay place to chunk it? Like,
Why was there nothing right there?
that is a great question. Why was there nothing? And so for the most part here, we didn't have, there's not a super huge amount of geologic record in a lot of these things, but B, what we can tell based on this banded iron is there just wasn't much oxygen in the atmosphere from here all the way to this point. And it wasn't until we started getting a little extra oxygen in the atmosphere that we started seeing a diversity of different things. Oh, and you know what? These stromatolites, I just noticed this. Sorry. Let's see here. These stromatolites, these are out over here in the billions of years, right around here. And these stromatolites are little bacteria pods, basically, that like mats, these bacteria mats that grow in shallow tropical oceans. And they still exist in parts of Australia, but that's pretty much it. But we find fossils of these, in some cases, going all the way back to a little over beyond 3.5 billion years. And these were the first things that we think were photosynthesizing because the modern ones photosynthesize. And that's what started kicking in oxygen into our atmosphere here, which I think is pretty cool. So there just wasn't much oxygen. There just wasn't much carbon dioxide, or there was a lot of carbon dioxide, but there wasn't yet enough things evolved to really use it and make stuff as best we can tell. So yeah, that's kind of happened. The oxygen happened. Maybe, oops, it's going to look a little messed up now, isn't it? Because I dragged it all around. But let me see, where was I? That's pretty close. All right, so we can chunk it up into like these points where there's life, there wasn't very much, and then kind of where the Earth forms. And guess what? This is how geologists pretty much start chunking and dividing things up too. And the evidence for all this stuff is in the rocks, and that's what we're going to be looking at as we move forward tonight and into the next couple of weeks is what is that evidence and how do we know that these things happened during that time? All right, so great job with this. Let's take 3 or 4 minutes here, maybe let's say 5 minutes. Let's take 5 minutes. It's 5:28, so let's come back at like 5:33 or 5:34, somewhere in that neighborhood, and have a quick little story time about how the Earth was made, and then we'll get into your next few little exercises. Then we'll take a quick break and do one last little thing, and then we'll be done for the night. All right, so let's say 5:34. All right, 5:34, be back. Go get a snack, go get a drink. All right, so it's like 40-second warning or so. Gather around and we'll start in just a few seconds. All righty, so here we go. So kind of to just follow up on what we just did in terms of that geologic time scale, kind of putting those breaks on, or the division lines basically of where there was nothing and then there was something in terms of life. That's how the original geologists broke it up, because back in the day, we didn't have radiometric dating. We didn't have a huge idea of what had happened in Earth's past, just because the science of geology was still fairly young. And so what they did break it upon was like where we find fossils and different types of fossils in the rock layers. Some fossils are very prolific, some of them are not. And sometimes you see that these rock layers have a bunch of different types of fossils, and all of a sudden above a different type of rock layer, they just stop and you never find them again. And so the geologists were able to assume back then that those species had just gone extinct, like they just didn't exist anymore on Earth, and that's why you didn't find them in any more of the rock layers. So over time, they ended up coming up with, get it, over time, that's a joke. Not really, but kind of was funny. They ended up breaking up the geologic or Earth's history, the historical timeline, into these different what we call eras over here on the right, these eras right here like this. We had the Precambrian, and then we had the Paleozoic, the Mesozoic, and the Cenozoic. When they made this, they had no idea how old the Earth was in terms of actual age, because they didn't have the tools and technology to date it. Now we do, and that's what we're going to learn about next week. But you notice to proportion here, the Precambrian is pretty much, there's nothing there. I mean, I shouldn't say nothing, but nothing interesting happened there. But there is a ton of time that elapses, and we have to take this top little bit here and kind of expand it and make it big so we can see the Paleozoic, the Mesozoic, and the Cenozoic all expanded out, and you get an idea of just what happened in each one of these times, kind of like we just did on the timelines here. So that's what we did. That's what we were looking at. And if you need like a cheat sheet to see some of the timeline stuff for your sketch notes, this is a good little slide to look at. We look at the first known fishes and stuff like that. I also, well, this semester I'm teaching a history of Earth and life. So if you want to know all about these different things, about all that stuff that happened there, that's a good class to take. I don't know if I'll be teaching it next semester, but there's a lab there too. Probably Dr. Sankey will be back. And she's an actual paleontologist, unlike me, and would have a ton of even more awesome information than I do. So anyways, that's geologic time scale. So we'll go from there into kind of a really quick brief history of the world here. And here's the brief history of the world. It started with the Big Bang, just like the what do you call it? The TV show, that's the one I'm looking for, the TV show, The Big Bang. Everything started with the Big Bang. And that happened about 13.8 billion years ago. And I'll show you how we know, well, actually, I'll just tell you right now. But basically, there's tons of evidence out there when we look at astronomy and we're looking at the way galaxies move and galaxies shift and stuff like that, that we can see all the galaxies are kind of moving away from each other. If we were to rewind time, all those trajectories kind of come back to one single point. We have a lot of what we call radioactive cosmic microwave background radiation that's constantly bombarding us from anywhere we point our telescopes in space, which lends us to believe that, you know, if there was a huge explosion, there'd be kind of a leftover dust and leftover radiation that is constantly coming through. And that's what these observations have helped us to understand, which is kind of cool and kind of crazy to think about. But what is our universe in? I have no idea. Nobody knows. Are there other universes? Is this the only universe in wherever we exist? Who knows? We can't tell with science yet. We don't have that information. But there's physicists and there's astronomers trying to make observations in space that will maybe help us one day figure that out. But that happened about 13.8 billion years ago, right? So Big Bang's about 13.8 billion years ago. And within that, it created tons and tons of the lightest elements that we know, which is hydrogen and helium. So it created a lot of hydrogen and helium atoms kind of out in the universe, and it exploded and expanded. And do I have my balloon? I think I threw it away. Dang it. Oh no, I have a balloon right here. Ha. But these dots represent like galaxies and things. As I inflate the balloon, or that you imagine this is the fabric of space, you can see that all these galaxies get farther and farther and farther away from each other. And that is what's happening in our universe right now. The first stars started collecting that dust right around 400 million years after the Big Bang happened. Prior to that, it was just too hot for anything to really glom together and get stuck. So it started cooling down enough where things could start condensing and dust could start smashing into each other. And that's where stars started being formed within galaxies. And so we just keep going on, going on, going on. And believe it or not, our universe is still expanding at this very moment. It's getting wider and wider. Every single one of the galaxies that we can observe is going away from us. And so we think the universe is still expanding. To what? We don't know. Will it rip and the universe just stop existing? I don't know. Will it come back and collapse on itself? Will it just keep expanding forever and nothing happens and all the stars just die out and then it's just a big mass of nothing? I don't know. So we're not going to have to ever worry about it like in our lifetimes or anything, but it's just, these are the questions that if you want to go do astronomy, that's what you could think about. So about 10 billion years ago, our Milky Way galaxy formed. It's a spiral galaxy. It's like 70 some thousand light years from the edge across. Yeah, it's about 70 some thousand light years across. So it would take you nearly 70,000 light years to get from one side to the other. And it's huge, it's massive. And within this cloud of dust of hydrogen and helium, it's all orbits around a black hole in the middle, a huge black hole. That's what keeps everything in the Milky Way spiraling. But within that, in those spirals of dust, that's where stars are born. All right. And so as these stars are born, they come together, they gather like these dust bunnies and they live their life cycle. And the bigger the star, the more fusion that happens inside these stars, and it creates heavier elements. So it like takes a hydrogen and sticks them together and makes helium. It takes helium and hydrogen, sticks it together and makes beryllium. And a lot of these stars, the biggest ones, can make elements all the way up to uranium. And that's how we got the elements that we see on Earth today. They all exist, thankfully, to some other star that one time exploded, making the heavier elements that are on Earth today. So like most of what we're made out of literally is the remnants of an exploded star, probably somewhere in the neighborhood of about 5.5 to 6 billion years ago. A star exploded like this. This is what we call a nebula or a supernova, right? Boom, a supernova remnant made this nebula. And within these dust bits, this is where new stars will coalesce and new solar systems will coalesce. And this is where planets will form around stars that come out of this dust. And so that's one of them. And there's another one that you can see pretty well with like binoculars, which is the Messier Nebula. If you look at Orion's belt, you'll see it in between there. And that's also another place where there's lots of stars being created. So there's billions and billions of galaxies out there. There's billions and billions, so hundreds of billions of stars in each galaxy. So it's just kind of mind-blowing, the sense of scale of all this stuff, right? So let's say we're in our Milky Way. Sometime around our Milky Way, after that other star exploded, created the dust that would eventually become us, our solar nebula begins to collect some of that dust right around 4.7 billion years ago, somewhere in that neighborhood. Gravity starts attracting it and bringing it together, kind of like dust bunnies have static charge and they get stuck together. And as they started coming together, they have momentum and velocity, and that causes things to start rotating and spinning. And eventually we get this big, what we call why can't I think of it? Starts with a P, not the proto-sun, but a protoplanetary disk is what I'm trying to say, which means There were no planets formed just yet because most of the hydrogen and the helium and things were going into the sun and making up the mass of that center bit of this protoplanetary disk. And it's going to keep swirling around and going around over time. And eventually within some of these rings here, you see on the outside, those dusts will start collecting and making planets outside of where the hydrogen and helium is that'll eventually make the sun. And it turns out most of the heavier elements, since there's more gravitational attraction, they kind of stayed closer to where the sun was. So that's why our inner planets are made up of heavier elements like silica. There's a lot of iron and nickel and stuff like that in our rocky planets. And the outer planets out here, like Jupiter and Venus and some of the, not Venus, Jupiter and Saturn and all those out in the outer belts, those gassy planets were sweeping up more hydrogen and helium and some of the other gases like methane and stuff like that. So how do we know that this is happening? Well, I'll show you a picture in just a minute. But basically we see in other galaxies, or not other galaxies, but in other parts of our galaxy, we can see protoplanetary disks actually in the stage of forming and creating new stars and seeing new stars kind of ignite and turn on, which is pretty cool. So this is basically the start of our solar system about 4.6 billion years. It took about 100 million years or so for all that dust to kind of coalesce and that sun to finally have enough energy of hydrogen and helium smacked together tightly. That fusion started. And once that fusion started, it started creating its own energy and heat. And that's what we have today. Some of it blew out a little extra dust and cleared the paths of where the planets are. But for the most part, a lot of that junk started smashing into the Earth and other planets and adding to it. And so how do we know this happened 4.6 billion years ago? Well, we're going to talk about absolute dating next week, but the clue here is meteorites. And these meteorites, hopefully it'll load here in just a second. This is one that I made a 3D model of a few months ago, or I guess last year now. But what's kind of cool is if you slice these open, and we'll look at this next week for sure, but if you slice these open, these rocks have not been melted or metamorphosed or changed since the formation of Earth. And so each one of these little dots right there is a millimeter. So this is about the size of your hand, the palm of your hand. It'll fit like a baseball maybe, but it's heavy iron and nickel. And if we slice this open, we can cut it open and we can take samples and we can see that there are little pieces that stuck together in here that would eventually make a bigger planet if it had enough time. But for the most part, these little pieces, when we measure them, in terms of age, are all about 4.6 billion years old. On Earth, we don't have very many rocks that are older than a few billion years old because of our rock cycle, and it keeps melting rocks and resetting the timer. But with these meteorites, the timer never gets reset out in space. They're just floating around until they bombard Earth. And when they hit Earth, if we can find them, every single one that we found measures out to be about the same age. So that's how we know that these are about the solar system started about 4.6 billion years. And if you want a cartoon version of this, that's even better than those pictures, is here's the dust cloud. Here's that kind of protoplanetary, or the protoplanetary nebula, or not protoplanetary nebula, but the protoplanetary disk floating around and spinning around like this. And all those chunks would come together and make bigger chunks. And then those bigger chunks would come together to make the planets. And that's what we ended up with today. All right. So here's the actual picture, or a actual picture of protoplanetary disk swirling around. This is going to be a star. This is probably going to be a really hot planet or something like that on the inside. And everywhere you see these kind of dark black rings, that's where there's a bigger object in there sweeping around and like sucking up all the dust and the bits to make more planetary stuff there. So after we had our solar system formed and everything's going for another 100 million years or so, we had what we call the continual heavy bombardment stage of Earth, or almost a billion years is what I mean, where just all of these extra pieces that were leftovers that didn't make it into the planets kept smashing into Earth. So it made Earth a very difficult place to live. Things bombing on it. The Earth's crust was still molten. There wasn't much of an atmosphere. So that's what was going on for a long time, right after the Earth was born. Then once things started settling down, the heavier elements in the Earth started sinking down into the core. So just like on Earth, density rules, or not on Earth, but on the surface of the Earth, density rules, where heavier stuff or more dense things sink and less dense things float to the top. Same thing happens with these elements. And when everything was melted and hot, the more dense elements generally went down towards the core. So we know today that the core is pretty much iron and nickel and a little bit of cobalt and a few other things. And we'll talk about those, how we know that later on in the year. But that's where it went, leaving us up in the top, minerals like silicon and oxygen and hydrogen and helium and things like that. Not so much helium, but hydrogen also up here near the surface. So that's where it started differentiating, started making the different layers of the Earth. And then a few 100 million years or 100 million years after the Earth formed, something the size of Mars smashed into us. And when it did, this is a simulation of what it probably did. It was like a glancing blow and allowed, let me go back and show you again here. It allowed the bits to coalesce and start orbiting Earth, because Earth still had a pretty good orbit, gravitational flow there. And that's what would become our moon. All right. So a glancing blow of a planet type thing called, similar to the size of Mars, glanced into Earth, blew off a huge chunk of the Earth's surface, and some of that then coalesced with whatever hit it. And that's what became the moon. And what's kind of interesting is the moon is almost chemically identical to the Earth, because they're made of the same rocks. They came from the same place, which is pretty awesome and pretty neat, I think. And we know that because astronauts brought moon rocks home when they landed there back in the 70s, 60s and 70s, I should say. So let me go back there. So that's how the moon formed. And then, oh yeah, somebody has a raised hand. Sorry, go ahead. I totally missed that. Valeria, go ahead.
When you said in the beginning that guys don't know what hit the Earth, it's the moon that hit the Earth? Or
That's a great question. So it was, let me go back to here. It was something about the size of Mars hit the Earth. So it wasn't the moon yet. So the moon didn't hit Earth, but there was something, there's like another, if I go back to like this cartoon, there was something else out in the realm of where the Earth was, that right after the Earth was pretty much done forming, another planetary body was kind of in near the same orbit and smashed into it. So it would have been about the size of Mars based on the calculations of like how much stuff got flung off, and they do all the physics and the computer modeling. So they think it's what we call a planetesimal, or a planet-like body, the size of Mars, just about or so, smashed in off to the side of Earth, a glancing blow of Earth. And when it did that, it blew some of that chunk of Earth off. Some of the things that used to be that planetesimal became incorporated with Earth. Some of it melted and blew off in the collision like this. And then it kind of orbited, that debris orbited Earth for a little bit, and over time gravity just kind of brought it all together and came together, and that became the moon. So something the size of Mars hit the Earth, and then the stuff that got blown off the top, that would eventually become the moon. If that makes, does that clear up your question?
It does. Thank you.
Okay, thanks. So yeah, let me know if I'm ever unclear, because sometimes I see pictures in my head when I'm talking, and sometimes the words don't come out to match those pictures. I apologize. For the most part, I think they should, though. So anyways, the Earth started cooling down. We started getting a crust on the outside of the Earth. And as it started outgassing and cooling off, our first oceans formed just a few 100 million years after the Earth formed. But it was really toxic gases at that point, like hydrochloric acid and things like that come out of volcanoes. So it took a lot of different time for different processes to happen for that atmosphere to kind of become not as caustic or not as toxic to us and for us to breathe, right? And so that's kind of how we got here to present day. That's kind of the beginning of when the oceans start getting here. And then when we looked at our timeline, it took another almost 4 billion years after the Earth formed before organized multicellular life started out and evolving and just started going crazy. So, I mean, life that we know it, or even life of like multicellular organisms, has only been just a super duper duper small chapter in Earth's history. I mean, there was billions of years where there was not much life on Earth. There was, water, there was rain, there were mountain building, all that stuff was happening, but without any witnesses, no life. And I think that's kind of cool and interesting to think about. So that's how we got here. And I promise you we'll be looking into some of the ideas of how we know this as we keep moving forward, especially in the last little bits with astronomy, this class. But what's kind of interesting is if you click on this link, it's a gigapan where you can zoom into this. And every single one of these bright dots that you see here is part of our Milky Way. That's a star within our galaxy. And within our billions of stars within our galaxy, pretty much every single one we look at, or not every single one, but many of the ones we look at, we now can find planets orbiting those. So what else is out there? Who knows? But there's so many light years away, we'll never be able to travel and see there. I mean, it takes, in some cases, 50, 60, 70 light years just to get from one star to the next, traveling at the speed of light. And we can't even come close to hitting the speed of light. So who knows? Maybe in the future they'll find ways of teleporting to places, but for us, it's just looking at it. And when we look at stars out there, if they're hundreds of millions of light years away, it took all that time, hundreds of millions of years, for that light to come and then hit our telescopes or hit our eyes when we go up and look at these stars at night. So we're kind of like time traveling when we go up and look at these stars. And we can look at those and see what other solar systems have done. We can see their evolution, and from that gain some experience of what to expect in our solar system moving forward. All right. So I don't know why that's there. We already took a break, so we're going to keep going here. So that's a brief history of the Earth. Good job. Now I'm going to show, oops, ouch, sorry. I ran over my toe with my chair. That was not good. But now what we're going to do is try to figure out and give you some clues to figure out how do we know how old the rocks are. And before we can do that and put an exact age, we're going to look at some sequencing and try to figure out how we know how old they are based on a few simple geologic rules. And then how are we going to know what stories they tell? Well, we'll get there as the year keeps progressing once we use these rules. But these rules are kind of like learning how to read a book, right? You got to learn letters, and then you got to learn sentences or words, then sentences, and then you can write these big chapter long books. And that's what we're going to be starting to do tonight, is kind of building our alphabet essentially to figure out how do we know what's happening. Okay, so what we're going to look at, these 8 geologic principles here. These geologic principles are going to help us decipher those pages. And so one thing to think about here is that the rocks record Earth's history. And so they record geological events like earthquakes, volcanoes, changing mountain forms, changing life in terms of the fossils that are in there. So that's what we're going to be looking at. So we're going to use some of these geological events to help us understand the past. Okay. And one of the things that I like sharing, this is a little fossil, it's about the size of my hand too, of a rock I found in Las Vegas a few years ago on a geology field trip, believe it or not, when I was still in college. So I guess it's more than a few years ago now. But anyways, this stuff, it's Bright Angel Shale. You can find it right outside of the city limits in Las Vegas. And it's about 500 million years old. It used to be mud. Shale is a type of rock that used to be mud, but it's been squished and compressed and turned into rock. And each one of those little lines right there, those are the footprints of these dead critters here called trilobites. And so trilobites were one of the most abundant hard-shelled organisms, one of the first most abundant hard-shelled organisms on Earth. They were the first ones to have eyes, which is pretty amazing. The first organisms on Earth that we know of that had eyes, that we can tell for sure. So to be able to hold this rock and like see these little steps, this was the bottom of an ocean 500 million years ago, where Las Vegas is today, where these little critters Nothing's related to them today, but these little critters were crawling across the mud, which I think is just kind of cool. That's a neat story. So how do we know that? That's what we're going to be looking at. Okay. So the first law that we're going to look at, or this first rule, is what we call the principle of uniformitarianism. And so when we look back in deep time, we assume as geologists and as scientists that the same laws of physics that happen now happened 400 million, or a million years ago, a billion years ago, when Earth formed. There's nothing to lead us to believe that processes on Earth were any different way in the past than they are now in terms of the underlying physics that runs things. So the principle of uniformitarianism means is if it happens today, it probably happened in the past too. So if there's rivers cutting canyons today, there would have been rivers cutting canyons a billion years ago, right? If there's like rain falling on the rocks and causing them to erode, that probably happened a long time ago too. Or there are oceans now, there were likely oceans then, and sediments falling out of them. So that's what the principle of uniformitarianism is if it happens today, it happened in the past, okay? The next one is called the law of superposition. And if I were to just take a deck of cards and throw them out on a table here, where do you suppose, and so you guys can just chat or unmute, where do you suppose I would find the card that was the one that I threw down on the table first? Where would we find that in this pile?
At the bottom?
You got it, at the bottom. And guess what? Rocks are exactly the same way. When we have layers of sedimentary rocks and stuff, the oldest ones are at the bottom, and then everything kind of piles up on top of it. And that's what the law of superposition says, is the oldest rocks are going to be at the bottom, the youngest rocks are going to be at the top. So here's Bryce Canyon. If I were to say, hey, which rocks, based on what I just told you, which rocks are older, which layer of rocks are older, the orange ones or like the light pinkish white ones, which one would you say was the oldest based on what you just know? What do you think?
At the bottom.
You got it, at the bottom. Ooh, see, I make these connections easy. Playing cards to rocks out in Utah. Yeah, so these rocks down at the bottom are going to be the oldest. And as we go up, these are all eventually we'll learn were sediments deposited in an old lake or an ocean side, and they built up over time. And so the oldest ones are at the bottom, and then the youngest stuff starts piling up as we move on. So that's what the principle of superposition says, is that in an undeformed sequence of sedimentary rocks, the oldest layers are at the bottom and the youngest ones are at the top. So if you go to the Grand Canyon and hike down from the top of the Grand Canyon down to the bottom of the Colorado River, you're literally time traveling. You're going from very young rocks or fairly young rocks down to rocks that are over 1 billion years older down at the very bottom of that, which is pretty crazy to think about. But all of these are sediments, and they were laid down in oceans or deserts and things like that. The youngest ones on top, oldest ones are down at the bottom. Another law or principle, I guess, that we can say is called the principle of original horizontality. And what that means is if we're looking at these layers of sediments or sedimentary rocks where things have been deposited like this over time, they're going to be flat, right? We don't ever, if you were to take a cup of dirt and shake that cup of dirt and then set it down, all those dirt particles are going to lay out, and eventually you'll have a fairly flat surface right there. And that's what happens with all of these too. So what this tells us is if it's not flat, if it's angled or crooked or something had to have happened to those rocks to make them get shifted and turned. So we always assume that if they're sediments or they're rocks that were made of sediments, that they were originally flat like this and not crooked. There's always exceptions to the rule, but for the most part, this is what we're going to be talking about. So here's an example of rocks that aren't horizontal, right? And here's me wearing the perfect, I guess, camouflage, the same colored shirt and shorts as the rocks. So it's hard for you guys to see me there. But let me ask you this. How do you think, so if these rocks, if I told you were originally flat, what process might allow these rocks to not be flat? What would cause them to curve like that?
Would it be like the water?
Oh, so give me an example. What do you mean like water?
Like maybe like, I have no idea, but like maybe like a river or something. And then I was thinking, again, I have no idea, but like wind or something, like strong winds or something coming through.
So you're thinking like ripples, like when a river goes through, like ripples in the layers. Is that what you're thinking, or?
Maybe no, maybe not.
Okay. Okay, well, maybe water like washed it clean, so, or not washed it clean, but eroded it so we could see the layers like this. But that's a good idea. And remember, none of us are geologists. Well, I am, but none of you guys, I don't think, are geologists yet. So we're just looking for ideas and seeing thoughts. So this is good for sharing. What are some other ideas? What might be some ways to take these layers and bend them up?
Maybe like an earthquake or tectonic plates hitting and crashing.
Maybe earthquakes and tectonic plates smashing. That's an idea. And I heard somebody else had an idea.
Oh, I was gonna say the same thing.
Oh, okay. Stealing everybody's thunder. So that's cool. So let's see. I have a stack of papers here. Let me move myself. So I have this stack of papers right here. Let's assume these are layers of sediments and like sedimentary rock. If I push my hands together or squish them, you notice I can get those layers to bend up. And exactly in order for that to happen, we have plate tectonics that we'll be learning about later, but also earthquakes happen in order to make that movement happen. And over time, we get some earthquakes, and some of those soft sediments or sedimentary rocks can bend up like this. So yeah, if I see rocks like this, the thing I'm thinking is, ooh, something squished those. All right, so that's a clue. And then that's one way. And believe it, I think it was Ariel mentioned water can also make curvy folds like this if there's big, huge currents sometimes, but that's kind of a rarer thing, but it definitely does happen. So you guys are all right. And another way of looking at it is like if you shuffling a deck of cards, right? You squeeze the cards, they kind of bend up on the side. Here's another crazy example. This is on the way to Kings Canyon National Park. Up on the road, like outside of Visalia and stuff, going to Kings Canyon. And all of these, believe it or not, were tropical reefs a long time ago, tropical like coral reefs and things like that, limestone, and something caused those to get squished and squished and smushed and really messed up and folded like that. It's really cool and it's really pretty if you ever get a chance to go out there and see it. So we'll be looking at these types of rocks, these metamorphic rocks later on, but yep, these were squished. All righty. Now, so that's 3. Here comes number 4, which are these principles of cross-cutting relationships here. And so these principles of cross-cutting relationships, what that says is basically if you have a fault, and a fault is like this crack you're seeing in the rock right here. We're going to talk way more about faults later on in the year, but this is kind of like our first exposure of it. But faults are a place where rocks break and then they move. All right. And the way we can tell these rocks have broken and moved is there's a big giant crack right there. And if you look on either side of the crack, these layers of red rock, they used to be together, but now they're not. They've slid. So what that tells us is these rocks had to exist before they broke. So that means the rocks were there and then the fault happened. And guess what? If you have a fault and the rocks break and move, guess what we feel that as? What do we feel breaking of rocks and movement? What does that feel like to us? What is that? The San Andreas is also a fault. What does that make?
Earthquake?
Yeah, you got it. Earthquakes, you got it. So yeah, so there was an earthquake here that sliced these rocks and broke it and moved it, and there it goes. All right. So that's one way. And then sometimes, and this picture on the right is from the Black Canyon of the Gunnison. It's one of the steepest canyons in the United States. It's pretty amazing. But this grayish, the darker gray rock there, that was kind of the rock that existed. And then some magma or something squeezed up from underneath it, like a magma chamber that makes a volcano. And some of its hot magma or some of its hydrothermal or hot water went through the cracks in that black rock, or that dark gray rock, I should say, and filled in those cracks with new magma that is, in this case, white. And so what this tells us is that those gray rocks, the dark gray rocks, were there first, and then the lighter, whiter colors came second. And this is what we call the principle of cross-cutting relationships. The stuff that cuts across the other rocks are younger. The fault that cuts across this is younger than the rocks that are there. And the way I like thinking of this one too, it's a weird analogy, but if you made a fist like this and then got some toothpaste and you put a toothpaste tube in your hand and you squeeze the toothpaste into your hand, it would ooze out of the cracks between your knuckles and stuff. That's kind of what's happening here, is there's stuff being injected into those rocks and they squeeze out the cracks. And so your hand and fist was there first, and then you squeeze the toothpaste into it to fill the cracks. And that's kind of what's going on here. All right. So I'll just show you this really fast. This is the 3 types of faults, just to give you an idea. You don't have to know this. We're going to talk way more about this, but I just want to show you how faults are made.
The block above the fault, called the hanging wall, moves down relative to the block below the fault, called the footwall.
There we go.
This fault motion is caused by tensional forces and results in extension. In a reverse fault, the hanging wall moves up relative to the footwall.
That's squeezing.
This motion is caused by compressional forces and results in overall shortening. A strike-slip fault is a near vertical fracture where the ground has shifted parallel to Earth's surface due to horizontal shearing forces. If you stand on one side of the fault and the block opposite you shifts left, it is called a left lateral fault. If it moves right, it's a right lateral fault.
And so those are how the Earth breaks, and we'll talk way more about that in like week 6 or 7 or something like that. But I just want to show you, when we talk about faults and we start looking at these cartoons of faults, that's how faults got there. Okay.
I have a question on that.
Oh yeah, go ahead.
So for those faults, like we would find like those faults in like different part of the world. So like would we find like I don't know, but like would we find like the reverse fault in California, or would that only be found like someplace else?
That's a great question. And California, let's just say, is messed up because of all the faults that we have. So we have lots of reverse faults. Southern California, Los Angeles is like the primo example of all those reverse faults. We have those strike slip, or the ones that move side by side. That's the entire San Andreas fault. And then we also have normal faults where things are pulling apart on the eastern side of the Sierra. So we have all 3 examples of these here in California. And that's why people come from all over the world to California to study geology, because we're awesome, but we're also complex and very confusing sometimes. But yeah, that's a great question. And that's why we've got to be so earthquake ready in California, because we have all sorts of faults that can create all sorts of earthquakes, and a lot of them are going to be damaging. And if you go just north of California into like Oregon and Washington, you have really strong and mega thrusts or reverse faults that are even huger, that can create the biggest earthquakes in the world. We have a lot to talk about there, but yeah, this is just kind of the background for that. And oops, sorry. And here's some background for how the magma can like intrude into different cracks in the rock. So this is what we call these intrusions, and how you get hot molten stuff cutting across like layers of sediment. So sometimes it'll go up and bend the rocks and not erupt. Sometimes it'll make these magma chambers and then escape to the surface and make volcanoes. But if it cuts across all these layers here, the layers had to be there first, and then the magma cut across it later. All right. So that's just some visualizations to help us imagine what we're going to see in our cartoons here in just a second. Okay. Oops, gosh darn it. There we go. So those are intrusions. Here's an example of some intrusions from Yosemite. So let me ask you this one. On the right side, let me ask you this. Which of these rocks is going to be the oldest rocks? Which one was there first, the gray rock or the white rock? What do you guys suppose here?
The gray rock?
Yeah, the dark gray rock. That was there first. And we know that because the white cut across it for sure. So these are like the cracks and filling it in. So this is in Yosemite. Another blip of magma came through after this stuff had already solidified and made that. And then on the left-hand side, there's my wife standing next to these. First of all, what do you notice about, I see lots of layers, like thin layers here in this picture. What's weird about those layers to you? What did we talk about? How did those layers normally form?
I may be wrong, but I'm going to take a guess. Is it because of they move horizontally with each other?
Yeah. So they formed horizontally. Yeah. Oops, sorry, my paper. So they formed over time, right? Sediment layers moving horizontal. So are they horizontal in this picture though?
Vertical.
They're vertical now. So as geologists, what that tells us is, oh, if they're not flat, they're not horizontal, something had to have happened to make them tilt. So maybe it was either squeezing, or maybe something broke off and they started hanging down funny or something like that. But yeah, something had to have happened to make these rocks go from horizontal to almost vertical. And then Mrs. H is standing next to this intrusion that cuts across all those layers. So we know that this intrusion is going to be younger or older than the rocks that it cuts across. What do you suppose here? So this intrusion, it cuts across. Yeah, you got it. It's younger. So because it cuts across everything, it's younger. So something happened. These rocks formed flat, they got tilted vertical, and then sliced like Zorro right through and filled in with new stuff later on, like a hydrothermal vent or something. So cool. You guys are pros, all right? And so here's an example of some cross-cutting relationships I saw like 3 weeks ago on our hike before school started. We have the granite with the cross-cutting stuff happening here. And you can see how big some of these rocks are, but it's all over the place out there, out in the wilds in California. And we'll get to see some of that later on. So there's also what we call the principle of lateral continuity that we're not going to talk about too much, other than the fact that erosion wears a lot of stuff away. And so sometimes you could have rocks that are exactly the same on either side, separated by maybe 100 or 200 miles because maybe erosion has washed things away in the time since they formed. So what we assume is just that this lateral continuity means at one time it was all filled in with the same types of rock before erosion happened. All right. So we just infer that it was generally continuous over a great distance a long time ago. So that's lateral continuity. Then here's one of the other big ones, and then we'll take another quick small break here, and then we'll finish strong. These things called unconformities. And so this is a weird where if I were to take some rocks that were flat and I push them up and make mountains out of them, rain and everything else is going to start eroding them down flat. And so in an unconformity, what happens is it's a time when deposition, or when we start depositing sediments, it stopped, because if you're on the side of a mountain, things aren't going to deposit on top of there unless that mountain's underwater. And usually they're going to start falling off, right? They're going to erode off and go someplace else. And so that's how we get these unconformities, where you get an uplift and then it erodes down flat. And then after it erodes down flat again, something starts depositing more sediment on top of it. And the one that we're really going to be looking at and talking about are called these angular unconformities. And the reason they're called angular unconformities is because there's flat rocks on top, and underneath the layers of rocks are at an angle. So they're angled, and it's an unconformity, which means there's a big period of time missing because rocks had eroded away. So let me show you. I have a picture, I have a video. All right, so here's what an angular unconformity looks like, and I need to drink water here. Sorry. So you have these layers depositing in an ocean over time, builds up these thick layers, and then maybe tectonic forces squish them up to make a mountain. That mountain erodes down, and then over time, maybe that area subsides or somehow gets underneath sea level. Oceans form, and they start depositing new stuff on top of that. So that's where we get, this is what we call this angular unconformity. And on this cartoon where you see these squiggly lines, like that dark, thick squiggly line that's not flat, that means there was erosion to have washed it away. All right, oops, come on. We also have some non-conformities, which we're not going to spend too much time looking at, but basically think of Yosemite. So if this was granite, like in Yosemite, all of this stuff on top of it has eroded away to make Yosemite. So it would be like what we see today. This would be Yosemite. And then if for some reason in 20 million years or so, Yosemite ended up beneath an ocean, there would be sediments starting to flow on top of it. And this is what we would call a non-conformity. But don't worry about that too much. All right, we just were caring more about the angular unconformity. And if you're looking at, I don't know why my pictures came out so pixelated, I apologize, but if you're looking at the Grand Canyon, what's pretty interesting is we have this really big angular unconformity underneath the bottom of all the layers that are horizontal. And these granites and all this other stuff that's down here, these are like 1 billion years older than the rocks that are right here, like this Bright Angel Shale. So these are like 500 million year old rocks, and these rocks are 1.5 billion years. And so something happened that eroded down for over 1 billion years worth of geologic history that we have no evidence of what was there. We just don't know. But what's kind of cool to think about is because we have all these angled blocks underneath the Grand Canyon like this, what we can assume is, man, maybe, just maybe, there's at one time a huge mountain range where the Grand Canyon is based on the angle and the tilt of these rocks. So we'll see if that's a plausible solution later on in this, not tonight, but as we move forward. But it's just kind of cool to think about. So all that was angled up and then eroded flat, kind of like you see here. And here's what a picture of an unconformity looks like in the wild. This one I found in Washington when I was out and about on a geology field trip with some other friends and colleagues. But you can see how the angled rocks are right here, and then they're more flat on the top. So that's an angular unconformity. We have an angular unconformity. This one's in Death Valley. So you can see these are angled kind of to our left, like, oops, to our left, like, is that the right way? Like this. Yeah, like this, right? They're angled like this. And then the layers on top are much flatter, and they're different types of rock. So that tells us another different type of period has happened there. So Death Valley is a cool place to see that. And if you want to see a non-conformity in California, if you drive up Sonora Pass, you can't go this weekend though, because the forest is closed until September 18th or so, something like that, because they don't want to have fires happen. Where the granites are, these granites are almost 90 million years old. And then these black rocks are volcanic mud flows that erupted about 11 million years ago. So there's a 70 million year difference between these rocks and this rock right here on the right, which is kind of slick. So now what we're going to do is we're going to do relative dating. And when we talk about relative dating is the sequencing or ordering of events using superposition and cross-cutting relationships and all that stuff. That's what relative dating is. That's going to be able to tell us, hey, the rocks down here are older than the rocks up here. Not in a specific age, but we'll be able to order the timeline in which things happened. That's what this is going to do. All right. So here's what I'd like. Let's take a 3-minute break, a quick break. Go stretch, go get a snack, get something like that, because when we come back, we're going back into our groups, and then we'll be pretty efficient with that. And I think we'll probably be done just a little before 7 tonight. So we'll be out just a little early. All right. And so let's say it's 6:21 now. Let's come back at 6, let's say 6:24, 6:25, somewhere in that neighborhood. Okay. So bio break, get some food, get a drink, and stretch, and be ready to talk with your group again in just a minute. All right, y'all back? You ready for this? So sorry, that was a lot of talking on my part, but we'll get to have small groups again and have some more fun now. So here is the next thing. So I'm gonna get this link, and I think this is gonna work for you. Oops, not this one. Let me get the right link. Where'd it go here? Relative dating practice. So here's what's going to happen. I'm going to pop this link into your Google Drive, but don't do any, or not Google Drive, the chat, but don't do anything with it yet, because I want to show you how it works. All right. So if I popped it into a new window, it's going to look like this, and it's going to say copy document. So yeah, make a copy. And remember, this is just for you to practice, but it's going to save this to a Google Drive. So everybody is going to be able to do their own thing here. So you make a copy, and then everybody's going to have this thing right here that looks like this. All right. And I changed the picture on this one from the one that you saw on our slideshow. But basically, geologists love going out. And if you're a sedimentary geologist, love going out and looking at the different layers of rocks to figure things out. Or if you're a paleontologist, sedimentary rocks have all the fossils in them, or mostly have the fossils in them. So you might be going to find fossils and looking at cool stuff like that. So what we're going to do in your groups is we're going to use all those different principles that we just learned. And I promise you, this is 1000% easier than it's about to sound. But we're going to be able to put into order all of these different geologic events that are represented by layers of rock here. So we're going to say what thing happened first, what happened second, third, fourth, and fifth, etc. Okay, so when you open up your slideshow, you'll see that there is a, oops, there we go, yeah. Oh, come on, sorry, trying to get my cursor here. You'll see that there are these green little letters here. And all you have to do is, as a group, you can have one person share a screen or do your own, it's up to you guys, but move these into the correct order and what's oldest and what's youngest. So the first one, this one's pretty easy based on the properties of superposition, right? And original horizontality. Guess which layer is the oldest in this layer right here? And we'll do a couple together with you before I cut you loose in your groups here. But guess which layer is oldest based on being at the bottom? And by the way, this is a cross section. So the tree on top is kind of like the surface of the earth, where the dinosaur that's like standing on it, that's the surface of the earth. And then everything else is like, if you shoveled down and dug down and scraped everything away, this is what it would look like. So at the bottom, what layer is at the bottom? Yes, I see A. All right. So you got it. A is at the bottom. And so then B would come next. And I promise you the letters will be scrambled up later on, but they're just easy to go for this case. So A, B, C, and D. We don't know how old these are, but what we can say is that A came first, then B, then C, and then D. And one thing to know, all of these different patterns represent different types of rocks. You don't have to worry about those right now, except for one, that is igneous rocks that we'll see in just a few minutes. Don't worry about these. You don't have to know them. The only thing that you need to know about these is it represents different layers of rock or different things happening in time, because the types of rock are different. So we just layered that. A, B, C, D, piece of cake. You guys, you got it. All right, that's the first one. Then the second one, then, let me ask you this. And I didn't scramble the letters here either, but if we look, we always want to start from the bottom and then work our way up, because the things on the bottom are the oldest. So in this case, A, I can see little bits of A underneath B, C, D, and E. Oh, do you have a question, Skylar?
Oh, no, sorry.
Oh, yeah, no problem. I just wanted to make sure. So yeah, A goes first, and then what do we notice has happened to B, C, and D here? I mean, they're not horizontal, so what's happened to them? So I showed you squishing can make rocks go up. Squishing can also make rocks go down like this too, if you squish it just right. So you can get folds of rocks that make these kind of U shapes too. This like we call a syncline. But in this case, B is the next layer, then C is the next layer, then D is the next layer, and all those layers had to be there, and then they got folded, which we're not labeling here. And we see this kind of crooked line, that means there was erosion happening. And then we got flat layers on top of it. And that's when E and F would go. So that's how we ordered. A happened first and then all the way through F. Now, let's see if you guys remember from all my droning here, what do we call it where we have a layers of angled rocks with layers of flat rocks on top of it? Do you remember the name of that specific type of feature where the angled rocks meet a flat rock?
Unconformity.
Yes, what kind of unconformity? Because they're at an angle, we call it a angular unconformity. You got it. All right. I know somebody was typing that. I'll just pretend like you did it. Okay. So this one here is a couple of other things I want to point out. Anytime you see a dark rock with like these little funny camouflage looking patterns there, that's supposed to represent magma. All right. This is like magma that squeezed up through there. So and then you notice the letters are not in order anymore. So how about you guys tell me this? Which letter should come first? What was the oldest thing that happened? What layer of rock is the oldest in this sequence? I see C. Do folks agree with C? Yes, I see C's. All right, good job. So C goes over there as the oldest. Then what would come next? What do you suppose? What layer is on top of C? Yes, then E, all right. And are you guys noticing? I see that this layer A cuts across all these, so it must be younger than those. Then D, all right, awesome. I see D. Then now, this one's kind of tricky. What do you think comes next? A or B? All right, so I see votes for B. So that would mean B happened and then A came up and kind of squeezed through those layers. Is there also another alternative explanation maybe? And not that the B is not wrong, but there might be another way to interpret this too. Who can make an argument for A happening first?
If we talk about, how if that is magma, what if A came in first and then once it touched, like if it was a volcano per se, once it touched the air, it solidified, it cooled down, and then B came in.
That is a totally perfectly logical explanation. And so either way, those are right for right now. We just don't have enough information to know which one is 100% correct. We'd have to go find more information, but each one of those is totally right. So good job. So yeah, you could go A and then B or B then A. It's up to you either way. So moving forward, here's how we solve the problem of knowing which one came first. All right. And that is with these igneous rocks, anywhere I put these little asterisks next to the igneous rock, that means the rock on the other side of it, the rock that the igneous rock is touching, it cooked it a little. So it came up, it was super hot. And when that magma oozed in between those other layers, it cooked just a small little bit of these other rocks. That's how we get marble, like to make statues and stuff out of. It was limestone that was then cooked by a little bit of magma intruding into it. So if that's the case, let me ask you this. If B cooked E, which rock, sorry, I have to use my nose, which rock is going to be the oldest in this layer? And then I'm going to put you in your groups after I show you one last thing here. Which layer would come first here?
E.
E, you got it. And E comes first because it's at the bottom of all these other layers. And we know that B came across and then cooked E. So B had to come afterwards. So does B, it doesn't go into C or anything else like that. So B would be next. And then it looks like we have an unconformity here or nonconformity where there's erosion happening. So then we have C, D, and A. All right. So I have one thing to show you. I'm not going to do the last three. So there's 3 other slides basically that you guys are going to get to practice with as a group. But what I do want to make note of is what these lines represent. These lines represent faults. Okay, so these are how we draw the cartoony faults right there. So this is what you're going to have to think of in terms of ordering it. Now, I says C here and C over here. That means this layer and this layer are the same. And anytime you see that, like here's a layer A, this is also layer A with these kind of brick patterns. Anytime you see those same patterns, but they've moved, that means there's been a fault there. That's a fault where it's broken and moved. And so I noticed that this fault cuts across G and this layer and this layer and this layer, but it doesn't cut across any of these other ones. All right, so this happened and stopped, and then we have more stuff happening and with a fault over there. So what I'm going to do is I'm going to give you about 15 or 16 minutes here, 15 minutes. And I want you guys to spend about 5 minutes on each of these, maybe share a screen and try to come up with the correct order for all of these in your groups using some of those ideas that we just used throughout this class. So which order's first, or which layer is oldest, which one's youngest, etc. And notice with the second to the last one, slide number 7, there's some asterisks there. So this intruded and cut across all those other things and cooked it. And the same thing happens for this one. They intruded and cooked that. And I don't know why I didn't put asterisks on this one. I forgot, but A cuts across all those other ones and cooked some of those too. So just something to be aware of. Okay, so I'm going to put you back in your groups. You guys are basically going to be starting then at, what is this, slide 6, 7, and 8, and working together to collaborate and figure out which ones are the oldest and which ones are youngest, and just dragging and dropping them over there. All right.
Is this something that we're turning in?
That's the next thing I'm going to mention. So this is for y'all to work together on, and on your sketch notes, remember, you're going to have to draw a cartoon like this and kind of put things in order. So these are practices for that. You don't have to turn this one in, but you want to have something that works all together by dragging them and dropping them and getting practice with this, if that makes sense. All right.
For the sketch notes, really quick, for the sketch notes, so do we have some for last week and this week, or the ones due this week were the ones from last week that we're catching up?
Yeah, the one. So yeah, so last week's sketch notes are usually due like today before class happens, but we'll have a few extra days leeway for that just because I'm still getting a few things organized. And then tonight's will technically be due before class starts next Friday. That's how that generally goes. Yeah, so you basically have a week to work on them after each class, giving you enough time, hopefully enough time to do everything here. Okay. So you should all have these copies. You might want to share a screen and see which layers it goes. I'm put the timer on for 15 minutes, and we'll be back, close out some last thoughts, and then set you free here for the night. Dang it, now I gotta find breakout rooms. Sorry. Here we go. All right, put the timer on correctly and we'll go from there. So have fun. Oops, let's see here. Let's see, Ariel and Morgan, were you in groups before, or did you come a little bit later? I can't remember.
I was in group 5, but I left Zoom because I had to move places.
Oh, no problem. Are you good? Can I put you back at 5?
Yeah, I liked that group.
Okay.
And I was in it, and then I left. I was at the doctor's office.
Oh, no problem. I hope you're okay. Are you okay? I hope.
Yeah, I just have like stomach problems.
Okay, no worries. Which group are you in, or were you in?
I left right when we were doing the group thing because
so you haven't been in a group.
No.
Can I put you in like let's see here. I'll put you in group 3. Is that okay?
Perfect.
Okay.
Thank you.
Professor, you're on mute. There's no one in my group.
No one in your group. Oh no. You're in room 7. I'm sorry. How about I'll put you in room number 4. I didn't see that. I'm sorry.
It's okay.
Let me toss you in. Let me see. Where did you go? Oh, you're in 7. So I'll move you to 4. All righty. Can you join them? Or there we go. Okay, good. Oh, Brianna, did you see a button at all or anything? Or
No.
all right, let me try moving you to a different one and see if it comes up. Let's see here. And then I'm going to move you back to 4. Yeah, you getting something in Zoom that says come to that room?
There's a button on the side that says join breakout room. I'll try pushing that.
Yep, try that one.
I got it.
All right,
Thank
cool. Good job. Thanks. All right, so welcome back, everybody. I think most folks are here, or 7 folks are here. More will come. Some are faster than others, so I want to give everybody enough time. All right, great job, everybody. I know those are kind of hard and difficult and confusing, so let me just really quickly first clear off some of my space so I can see things here. So let's go over some of these answers really quickly, just to make sure you have these in your back pocket going forward. And there we go. And we'll see what you have. All right. And so you can watch the video for this if you need to, or you can change these on your own later on if you want. But in this case, for this one, the oldest layer is going to be G, right? So G is on the bottom here, and then C and A are on top. So C and then A, and then in this case, we had F. And what happened here was there was a block of rock that kind of went down like this, and there was F also on top of E at one time, but everything eroded away. And so we don't see any F on the top of A on this side. So that's why it's there. So then there was erosion. That's what we see here is there was erosion. And then I noticed the fault. That's the other thing. The fault B cuts across all that. So that comes next. Then the next fault I see, man, it cuts across all these layers, even the top ones. So for me, I know that's going to come last, right? Because it cuts across everything. So I'm going to put E up at the top. And then after we have the B cross cutting, then we had the layer H, and then D.
I have a question real fast.
Yeah, go ahead.
For the line that's slanting, like by A and E,
this one right here.
Is that what caused part of the H on the left-hand side to move like that in D?
Exactly. Yeah. So this is the fault. So this line where you see the things happening there, that's the fault. So literally there were big blocks of rock there, and this will become way more obvious when we get into the fault. But yeah, it slid down like this kind of. I don't know if you can see my hands moving, but it slid down. And in order for that to happen, there was an earthquake. So basically what you're looking at here is kind of like a fossilized earthquake. that records a movement when this was slipping down like that. Yep, but that's exactly what happened. Good ideas. And so we'll see here, you may not be too familiar with all these concepts and terms yet, but this is just the first dabbling of it. And we're going to get into it a lot more in more detail as the course goes on. But I want to start kind of just putting little breadcrumbs out there and you getting used to some of these ideas before we get too crazy with some of the things that we see. So at least now you'll have some background operational information moving forward too with some of that other stuff. So in this case, oops, sorry. Had a delivery that was late. In this case, the oldest thing that we're going to see here is not layer C because C cuts across all of that. So the next oldest one, or the one that seems to be on the bottom everywhere, is layer D. So I'm going to say D happened, and then it looks like H is on top of that. And then it looks like A was on top of that. And so let me ask you this then. Something happened where D, H, and A got squished and was able to make layers that look like this. So there was some squishing there somehow. But what comes next, do you suppose? Do you think C comes next, or do you think G comes next? And what's some evidence that we might use? So what came first, the magma intrusion or the fault on the earthquake? What do you suppose? I see a C. Somebody says C.
We were thinking that maybe the C with the, what is G called again? The fault?
The fault,
that the
yep.
fault happened and then allowed C to come in. But we had a couple different.
That's a great idea. And if there was a fault that happened and allowed C to kind of come in, they would probably be kind of oozing from a source like this. There'd be probably like a magma blob over here.
So,
oh, go ahead, Valerie.
One of my group members, she mentioned how on a little bit of the A layer, there's like a little part of C at the top right there, which means that C came in first and then G happened.
Good eyes. Yeah. So in this case, yeah, it's really hard to tell, but if you stared really close, there's a little bit of C up there. So what probably happened is this is the magma chamber where C was kind of oozing from. So this is like the big pot of magma that was squeezing out this way, and it cut across into A. And then you notice there's some up here too. So what we think probably happened then is that came through and solidified, and then the fault G cut across it. Yeah. So in this case, the magma was right first, and then G did that. But I got to say, there are lots of examples, especially in Death Valley, of where faults have happened and earthquakes have happened that have allowed magma and stuff to come to the surface to ooze in. So that is also a good idea. In this case, it's not the one that happened for this particular cartoon, but it totally does happen. So that's good, massive points for you there. All right. And then we have F, and then we have I, and then we have B. No lie, it's a fib. But what happened to all these? They're not horizontal, so something had to happen to make them like this. We didn't necessarily put that in the sequence, but eventually something happened to make them tilted and then eroded flat. And then the last thing that happened that came on there was E. All right. So there we go for those. And then I'll just go really fast with these ones over here. All right. So it turns out that in this case, I don't know why H was down there first, but O is first, then H came and cooked everything, and then B, and then L, this one was a long one, and then J, right? And then all of those were, oops, and then A, I forgot A cut across there. And then all of that was sliced by F. And then after F happened, then we have some of this stuff happening, which is M, more layers of M, and that's like sandstone, and D is like conglomerate, these cobbles. G, I don't know what kind of rock that's supposed to be. And then N, and then E, and then cutting across all that is layer I. Whew, but it doesn't go all the way to C, so it stops right there, and there's something happened in erosion and all that kind of stuff. So then the last one will be C, and then modern day K happening right there. So that's how all of these go. And you can use any one of these that you want in your sketch notes to like make that simple cartoon of this part. And you can talk about, oh, maybe this is not originally horizontal, it's angled. So there's an angular unconformity, which tells us something squished it at some point to make it angled. But this is the first way we start unraveling the clues of what has happened in Earth's past, is we start putting these in order. And then next week, we're going to start adding in some fossils and actual relative or absolute dates where we can say for certain, this is 500 million years old, or this is 333 million years old. That's what we're going to be looking at next week with that. So we're going to skip for tonight. We'll come back next week with correlation, and correlation is a pretty cool thing that basically allows us to match rocks from one area to another and tell a bigger story. But I do want to end by being able to show you in your sketch notes, it asks and talks about doing this giga scan, this giga sketch. And when we go out into the field, we can't do that this year because of COVID or anything. But when we can, ideally, this class would have had a field trip with it too, that we all would have gone with some of the other sections, the Yosemite or something like that. But we'd go out, and one of the things we do is kind of sit and sketch an outcrop and make a little cartoon of what we're seeing in front of us. And by drawing the cartoon and visualizing and seeing what the heck is there, it helps us have a better understanding of, or helps us think at least about what is going on in front of our face. It makes us pay attention to details. So here is an example of an outcrop, a real life outcrop where you can see an angular unconformity. Oh, Maritza, go ahead.
Sorry, before I forget, so for next week before class, are we supposed to have 2 sketch notes, one for last week, one for this week, or just?
Yep, that's
So
correct.
What did we miss last week?
So if you missed oh, that's right. I kind of emailed back. So if you missed last week, some things you can do is you can watch last week's recording, or in the modules of, and I have to go to the modules anyway to show you where this is. But in the modules here is where you can find all the information and like the links for the PowerPoints and stuff like that to help you out with some of those from what we did last week. And if you need help on how to set up the sketch notes, you click on create your sketch notebook right here, and it'll open up and show you how to do it from there. So we have a few extra days. Like don't stress, you know, I'm sure there's a few other people that need to add a few things, but basically all you need to do is, and I don't think we got to this big idea here last week with the 3D rock model, so you can just ignore this one. For the other class got to it, so I'll leave it up for them. But basically all you have to do is this one. So you might have to watch some of the video from last week to get some of the ideas from this. And then for this week, here is those ideas. So we talked about the geologic principles. You guys did some relative dating. We talked about how the Earth formed. We talked about the major timelines of events. You just got to choose 10 of those from the timeline that you might want to sketch and look at. So you can use it, the one we made in class. You can use the timeline that we've looked at on the lecture notes, kind of the colorful straight one that I showed you. But for the Giga sketch, here's your 3 examples down here. Just choose one of these links. But if you click on the link, where it takes you to is a gigapan that looks like this. And what's pretty amazing about gigapans is if you click this arrow or the expandy arrow to make it full screen, you can drag it. And then these are made by, they take like 300 or 400 different images zoomed in really close to the rocks and give it a second to kind of enhance itself. And then the computer stitches them all together to make one giant picture that you can then go across and look at in pretty high detail from far away, which is pretty amazing and pretty cool. So let me see here, sorry. Oops, somebody got bumped and is coming back. So what I would like you to do is just focus on one small area of one of these different places. And oops, doggone it, where'd it go? That's what I gotta do. I gotta make this small again. You can choose, where we go. The Moab fault, you can do like the tonal away fault, which is, or not the fault, but there's some squiggly layers here and somebody got cropped out right there as they're looking at it. But the idea here is we want to make this cartoony, all right? We don't want to make this look like an actual like piece of artwork or anything like that. So to give you an example, here is the Moab fault. Like here's the example of the Moab fault that I have here. I just kind of focused in on this area right here. And what I did was, oops, tongue on it. I was able to just draw it like this. And then I labeled the layers like, oh, I think all these layers that are the same color are A, and I think all these other layers that I think are the same color are C. So I just want you to make it cartoony and based on what you see. Don't get caught up in the super fine nitty gritty detail of any things, but just kind of look at some of the layers. So I'm thinking at most you'll have 6 or 7 layers no matter what you do. And I should show you the last one here, which is Deer Mountain. This one too, I mean, I can see there's like some angled stuff over here. There's flatter layers right here. Don't get caught up in drawing every single like grain of these bigger rocks or anything like that. That's not what we're looking for. We're just looking for you to make a cartoony sketch of, I mean, you could focus in on this area or focus in over here on this area or something like that. Don't have to do the whole thing. You don't have to put in all the detail. Just trying to make a cartoon sketch. Order the layers that are there, like which one is oldest, which one is youngest, based like you can do A, B, C, D, and E, you put your own letters on it. And that's what we're looking for. And if you notice things like maybe an angular unconformity, maybe you say, oh, hey, there's an angular unconformity there. Or if you notice a fault somewhere, maybe you make note of that. All right. But it's going to end up looking something similar to this. All right.
If we get it wrong or it's like not correct, do we get marked down points, or are you just doing it like based on like if we try our best?
It's so this one, for because this is the first time that you guys have ever done it, this is basically trying your best and doing what you see, and it's going to help me see what you see and what you're interpreting. And when I get the sketch notes and I look at them, I'll make a few comments here or there and say, oh, this was great, or like maybe you can add a few things here or add a few things there. And that's what we'll look for. But yeah, I'm not going to be marking down as long as the thing that you follow is if you give your layers letters, relatively date them basically, and then give me a couple of examples. This is what I'm really looking for too, is what principles help you order those layers. So like oldest ones were on the bottom, maybe they're horizontal, maybe you saw cross-cutting faults or something, just like you were doing in kind of these cartoony sketches. You're just kind of transferring over to here, and it's just doing your best. It's not to freak out. It's not like the world's going to end if it's, you know, looks kind of funky. That's what it is. It's our first time practicing it. It's our first time doing it. So I want you to feel comfortable just writing down what you see and sketching what you see, and you'll be surprised what details you start picking out, zooming in and looking at stuff, which is kind of interesting. So if I were doing this one, I might do like kind of a fat layer of like maybe let me draw really fast and then I know we got to go. Doggone it, where's my line? Here we go. Like this is what I would maybe kind of draw if I were doing something like this, is I would separate the layers out something like this, and I guess that line disappears. I apologize, but just big blocks, not super duper detailed. Okay, that's what we're looking for. And for this one, the layers I notice are kind of wavy and crinkled. So what do you think maybe made that happen? Are they originally horizontal? If they're not horizontal, what do you think might have caused them to not be horizontal? So, oh, is this class being recorded? Yeah, this is totally being recorded, and then you can totally watch it again later on. So it'll just take a few hours for it to like process and get uploaded. Maritza, do you still have a question, or did I answer that? Or
Yeah, you answered it. And then after that, we just take a picture and upload it on our copy that we made online.
Yep.
On the PowerPoint.
You totally got it. 100%. Yep.
Thank you.
And then, oh, go ahead. Question. I have
for the relative dating one, we can use one from like class, right?
Yep. You can use one from
or
class.
look one up or something.
Yeah. I would just use one from class. You could look one up. They might be out there, but yeah, just use one of those cartoons that we did in class, and that's totally fine. So with that, holy moly, we're running right up against the edge here. Let me give you, you don't have to do it if you don't want, but sunshines and blues are appreciated. So it helps me understand things. So here is the Jamboard. If you want to go there and go to the sunshines and blues, you can leave a yellow sunshine for if anything went well, blue if anything sucked. And then I hope you have a really great 3-day weekend. I hope you're able to stay safe and stay well and healthy and enjoy a little time off without too much smoke. So have a good night, everybody. And I'll stop recording here and see you later.
Professor?
Yeah.
Sorry, I have a quick question.